Hello, everyone. Everyone hear me well? Great. So my name is Ran Dubin. I'm a PhD student from Ben Gurion University, Israel. My PhD advisor is Professor Ofer Adar, and my PhD special advisors are Dr. Amit Vir and Dr. Ofir Pele from Ariel University. I just submitted my PhD thesis 3 days ago, so I'm extremely happy to finish this long journey at Black Hat. The name of our title is I Know What You Saw Last Minute, and we are going to investigate together YouTube video traffic, encrypted network traffic, extracted from Chrome browser with HTML5 player over HTTP2 encrypted application layer. Well, okay. My research is all about how to optimize HTTP adaptive streaming. And since encryption is such a huge part in today's networks, we investigate how can we understand what is the content inside the encryption. What is the quality of the video you're viewing? What is your quality of experience? And while researching this, we found very, very interesting patterns in the data. And this is our story today. Currently, I'm a senior data scientist at Secular, working on crowdsourced malware classification problems. And our agenda is as follows. We are going to discuss what is a motivation, what is a scenario we are speaking about, what is our problem and why we present it here at Black Hat, how can I know what video names or video titles you actually saw last minute, and how this work is actually different from other related works. We show the proposed algorithm and results as usual. So the motivation is pretty clear. Google encourages network privacy. It is reported that 70% of Google online traffic is encrypted. Google encourages others to do so by giving a ranking boost in their search engines. Now, a well-known fact is that HTTPS keeps your data anonymous. This means that the internet service providers, your ISP, can't snoop your traffic. Let's try to break it. So our scenario is a passive sniffing. As you probably know, passive sniffing is used by the ISPs in order to understand which application you're using, how much data you're consuming, what is your quality of experience from the different service you're using. However, they are also created an open source intelligence vector from your traffic. They are using your search history, your visited sites, and they sell it to third parties. It's interesting to say that last month in the United States, the FCC acknowledged this problem, and a new law now prohibits the ISP to sell your traffic without your permission. This is very interesting. However, your ISP is not the only one who have access to this data, to your network traffic. Your government or maybe others have this access. Now, if you can create an open source intelligence vector from YouTube videos, we actually can learn a lot of interesting things. Now, we all know that YouTube is the world's social largest video platform. It's not only used for pop music, right? It's used for propaganda, demonstration all over the world. Now, if you can take a set of videos that belong to a specific group, let's say a terror cell like ISIS, and we can actually point it out which users consume those videos, we can create an open source intelligence vector that can give us insight that was lost until 2003, when YouTube actually started using the encryption. Now, how are other scenarios possible with this data? I'm sure you can think about them. So actually our purpose is to show you that HTTPS, HTTP2 is not enough in order to keep your viewing habits, in order to protect your viewing habits. Now, our contribution is as follows. We have a very large data set that is already available for download, so you can play with it. We have a data crawler that enables you to put any URL, to download it, save the encrypted pickups, the capture of the data, and extend it to different titles or different problems domain. We are actually investigating videos, but maybe it's possible to other social media data. So with this tool, you can already have a head start. And we will show you a new traffic features that represent the data and the classification algorithms. Now, before we begin with the rest of the details, I want to talk about a common mistake. A lot of people ask me, Ran, what is the problem? You see, you have here, I have a better pointer. You have here the HTTPS, and then you have the URL. In the end of the URL, you have the video ID tag. You can use the HTTP headers that are visible in the network, extract it using a deep packet inspection, and you're done. The only problem, this is a common mistake, it's not true. When you're using with your browser and you're surfing with HTTPS to any site, the first thing you have the SSL TLS handshake. This actually protects your data. Therefore, the HTTP headers are not visible in the network. So how can I know what you saw? So first, we need to understand how YouTube videos are encoded. Then, we need to understand how the player requests the data. After that, we need to understand how the data is distributed in the network and what patterns does it create. If we can take all those things together, we can create a great machine learning classifier that will tell us which video title you actually saw. So let's start investigating it together. Before, let's talk about what is it, HTTP adaptive streaming. HTTP adaptive streaming is a solution for mobile and fixed networks when the bandwidth tend to fluctuate and you request high quality video. In the next seconds, your channel bandwidth decrease. Therefore, your player won't be able to download the video in the high quality and would rebuffer, and your quality of experience will decrease. So, what was the solution? We take high quality video and encode it in several quality and representation layers. Each is independent, encoded in variable bitrate encoding, and has different quality and resolution. Then, each quality representation is segmented to fixed segments. 1 second to 15 seconds depends on the configuration. This is a general purpose of how HTTP adaptive streaming works. Okay? Now, the player requests video resource Z from the server and receive a manifest or media presentation description, which indicates which quality and representation layers exist at the server. Then, in the player automatic mode, step after step, the player algorithm estimates the network condition, the playout buffer, and based on his algorithm, select which segment will give us the maximum quality of experience. However, YouTube specifically doesn't work in very large segments. They work in a granularity of very small segments using HTTP byte range request. This gives them the ability to ask a specific small chunks of the data. And how this data behaves and how we request the data, we need to investigate together. Now, if we take Wireshark and capture the data, we can see that we have two different possible modes of operation. The first one is the automatic mode. In this mode, we let the player to estimate which the quality will be the most suitable to download. We can see that traffic is illustrated in high traffic burst and a silence. In the beginning, we don't see it very well. Why? Because we have several different flows that helps the player to download the video faster. Each flow is represented by a 5-tuple representation of source, DSIP, source, despot, and the application type, which is TCP. Now we understand how the video in the automatic mode looks like, but we don't understand still what is the content inside each burst, and we don't understand how the player requests the data, because we can see that the throughput of each burst is different, and we don't understand why. Now, there is alternative mode. It's named the fixed mode. In this mode, you request from the player a specific video quality. Since the player knows what quality to download from beginning until the end, he downloads a 3 minutes video very, very fast, and after around 40 seconds, the video actually is downloaded fully. So The problem is that in this mode, we have a single variable bitrate because we select a specific quality, for example, 7320p. In this mode, we have multi-variable bitrates, since we have several variable bitrates that are possible to be selected. So this case is much more complicated, and we want to check this one out. Now, Wireshark is a very good tool to examine encrypted network traffic. However, sometimes it's very hard to filter out different information. Then if you're using Fiddler Web Debug Proxy, you can filter out different data and to see what is the behavior in a time span. So let's filter out only the video and audio and only the video. We can see here and we can see here something very, very interesting. First, we can see, for example, that this flow and this flow are not the same. This gives us indication that we have a mixture of audio and video in a single flow. We can see that the amount of data and the time span of the request. This gives us indication that we maybe will not be able in the encrypted network traffic to understand and to isolate each one of those requests. You can see we have 3 different requests, and here we have 2 different requests. Can we isolate each request and understand it? In the network traffic, since they are the same flow, and with HTTP2, which is a multiplex application layer protocol, we will not be able to distinguish between the different data. And this creates a complication to the classification. Now, we have to remember, it's HTTP2. There are other things, other messages that can come in each one of those flows, and we have multi-variable bitrate. Each flow can have several different qualities from our representation. So this is additional complexity. Now, let's try to understand how the player requests the data and what is the effect of its byte range request. We take 3 different networks, the same computer, the same video title, and the same video quality, and we filter out only the video in this graph. And we can see that the behavior is very, very interesting. We can see here, we all start in the same byte throughput, which is very limited because of the TCP window behavior. Each flow, based on the TCP window behavior, is increasing every RTT in general. So we can see that they all start in the same location, but when we request more data, the variability of the request is very, very large. We can see we have 2 similar downloads, but they're only similar. They don't have the same exact values. And we can see the third one is actually shifted. Each request is very variable. It's actually different. And this is added complexity since the request of the player can be dependent maybe in the network conditions and in your quality. Now, how this works is different from other related works. Well, most of the application classification problems actually discuss how to differentiate between YouTube, Twitter, Skype, BitTorrent. There are many, many different works that look at the same problem domain. However, very, very few related works discuss what is the content inside the encrypted application. So Wright et al. Investigate the voice over IP traffic for language identification. The audio is encoded in variable bitrate quality, and he exploits the variability of the encoding. Liu and Sapones did similar things with video titles. And they did it on RTP and TCP flows. However, our work is actually different. Why? First, we have the complication of the HTTP byte range request. We have a multi-variable bitrate and not a single variable bitrate quality. And it's HTTP version 2. We have different information in each flow. There is possible for it. So what is our solution? First, we need to understand what is the packets, what is the traffic flowing in our system. So we divide it into 2 steps. We have the connection matching, which is responsible to understand if a connection is new or it's ongoing. If it's new, the next model will be the deep packet inspection model. And since the network is encrypted, we will try to understand which application is it based on the client hello message of the SSL/TLS, and we try to understand based on the service name indicator field what service the player requests from the server. And we will see that for YouTube, for example, it's Google Video. So we can filter out only the content we actually want. Then each ongoing flow will go to feature extraction. Since we need to represent the packets, we have a lot of different flows, a lot of different packets. We need to create a structure that a machine learning process can understand. So after the feature extraction, we are creating a pre-processing and a classification algorithms that we are going to discuss now. There are many, many different kinds of features extractions for application traffic, for intuitive application traffic. There are about 70 very well-known features. Most of them are initiated based on the packet length, different time delays, and throughput. This is the base features, and you are many directions, many variations, many statistic operations you can do about them. But those are the basics. And those features are great. They are great, but in order to understand how to differentiate between different applications. But if you have the same application, the content, those features will not be able to represent your traffic very well. So we needed a different solution. After investigation, our preliminary work that actually tried to classify what is each peak video quality, we understand that in order to understand what is the title we want to classify, we need to represent it as we see it, bit per peak. And this is a representation. We actually sum all the data of this burst, and when we see silence, there is a total silence in this YouTube traffic, we say, hey, this is the feature. Now, why we use it? First, it illustrates the traffic as it is. Very simple, available for real-time classification, and we will show it in the white paper. I don't think I have enough time to show it here, that it's actually robust to packet loss and delay. Now, let's take a single video title which have 90 different downloads, okay? We can see in the horizontal line, we have the bit per peak feature index, and the vertical line is our different downloads. What can we learn from here? The first thing is we can see that the first and second index have low variability. There are two reasons for that. The first one is the TCP window limitation, which actually limits the amount of data the server can send. Now, the second reason is we have actually a mistake in the beginning. Since those peaks are coming very close, we are not able to distinguish between them. And sometimes you can see it very well here, that sometimes we classify a single peak, and sometimes we cannot, and we have two or more traffic peaks in the beginning. However, from the third peak until the end, we have very high variability in the traffic. This means that a vector classifier that is dependent on the order of the data will have a lot of trouble to understand and differentiate between different applications, even in the same title, because the data variability is actually the entire bitrate range. And this is a very big complication that we need to solve. Now, in the pre-processing, we actually try to solve the data variability. So if we can understand and estimate which one of those peaks is an audio peak, we can decrease the overall variability of the data. So based on the field research, we found that audio peaks usually are lower than 400 kilobytes. So if we can extract them, we can help vector classifier to classify the data better. But since 2013, YouTube are started to work with a single audio quality, high audio quality, with all their video qualities available. Now, the bitrate request behavior of the audio traffic It's much less variable. It's not the same as the video, which we can see high variability. Therefore, if we can create a classifier that knows how to exploit the low variability of the audio, we can actually use it as an anchor to the classification process. Now, we propose two different algorithms. The first one is a support vector machine, uses a radial basis kernel function, and it receives the bit per peak features as we saw in the matrix. Wait, thank you. And we have our proposed solution, which based on the nearest neighbors algorithm, which is a similarity classifier, which receive the bit per peak set features, which I will define shortly. Now, there are a lot of things I can say about SVM. It's a really good classifier, but as I presented earlier in the feature matrix of the single title, classifier which depends on the indexes of the data, and since the data is such a variable, it has such a strong variability, those classifiers will have a lot of difficulties to classify the data. Therefore, SVM, random forest classifiers that are usually very, very good are not giving the best results in this case. So why do I explain this? Well, the reason is that if you are using our next classifier as a feature to the SVM classifier, you can create a very, very strong classifier, and this is our new work that we are going to work right now. I want to explain what is the bit per peak set features that I discussed earlier. Let's define Sij as a set of bit per peak without any duplication. This is the set extracted for each vector, where I is the video title index and J is the stream index. If we have 90 download copies, the J will be 1 till 90. Now, let's define what is the nearest neighbor similarity algorithm. The similarity of two sets is defined by the size of the intersection. Now, for each title I, we're trying to understand which copy J give us the maximum similarity. Then, for each title I, we're trying to understand which of them give us the maximum similarity, but with the result have to be larger than the threshold. The threshold was set based on the cross-validation, and not surprisingly, the threshold is 2. Why? Because of the TCP window behavior and the way we extract the feature. We have 4 available datasets that you already can download. We have the train test sets, which includes 30 video titles. Each of them have 100 copies. We separate them for training and testing, 90 for training, 10 for testing. Then we have videos that are outside of our training. This means that there are videos that we don't know them. We want to classify them as unknown. And we have 2 additional data sets that actually try to understand if our feature is robust to packet loss and delay. I don't have enough time to go over them, but they will appear in the white paper. Now, let's try to understand what is a classification accuracy using different data set sizes. We can see for a single copy per title, per video title, we already achieved 78% accuracy. If we increase the datasets to 5 copies per title, our accuracy actually raises to 92% and go on. If you have a large dataset, you can be more robust to unpredictable network changes, the network quality changes, and larger datasets will help you to overcome them. Now, let's try to understand what is a classification accuracy. And we have both algorithms, the SVM, which achieves 70% accuracy, but is less suitable for this problem, so I want to discuss a bit about him a lot. But in our suggested solution, we have 98% accuracy. Now, there are two different errors we actually have in our dataset. By the way, if in the diagonal line, it should be totally red. This means that we have 100%. we can see we have arrows. I don't know how well you see it right there and right there. We have arrows between the different titles. This is the worst mistakes we can have. Why? In a real system, you cannot understand if you have a mistake or not in the traffic set it's encrypted. So our future work try to minimize any of those mistakes. Now we have additional mistakes when we say that we have video title I, but we were unable to classify it since it doesn't pass the threshold. In these cases, we say it's unknown. In these cases, only a larger data set will help us to overcome those problems. We tested the 200 video titles that are not found in our training testing, and we finally achieved 100% accuracy. This is, I say, unfortunately 100%, because we already saw earlier that in our train test, we achieved 98%. So this is actually a 200 video titles that are already available in the site, but we tested our algorithm with thousands of videos, and we estimate that in a real network, our classification accuracy will be around 92%. This is one of our ongoing results of, instead of 30 video titles, we use 100 video titles, and we see that we get accuracy of 93.6. There is something very, very interesting to show you that happens exactly here. We have two different videos that are slides, and they are very, very similar in the traffic patterns. As a result, there are around 50% mistakes between the labels between them. Now, this actually means that our algorithm is good for variable bitrate traffic. And if you are using a static video, such as music, when you have single side and only speaking voices, our classifier will not give you the best solution. For conclusion, we actually created an open source intelligence vector from YouTube video traffic. We show you that HTTP2, even that the traffic is encrypted, we still can understand what content the user requests. Our algorithm presents 98% accuracy, and our contribution is crawler, dataset, and algorithms. Any questions? Thank you very much for coming.